What's up, people?
Hey everyone, Eigen folks.
Yes. Hello, guys. So, just to start us off, make sure you like, share, comment, subscribe. What's all this stuff I got to say? One.
Twitter, the socials, yeah.
Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. Thank you once again to the patrons. You guys are the best. And also, guys, if you are not a Patreon subscriber yet, check us out. Eigenbros on Patreon. Just donate us $1 per month, and you can get a free 30-minute podcast. Well, I guess not free.
Yeah.
A 30-minute podcast every week.
Well, you're free to listen, but
Yeah,
that's up to you.
it's not necessarily science related, so you guys should like us a lot if you want.
Yeah. It's more of like a culture. We dive a lot into culture, off-topic stuff. Sometimes we do dip into science stuff.
Yeah. But more seldom than frequently.
But it's usually more scattered than the programmed podcast, I would say.
It's more like the older podcasts.
True. A return to form, so to say. But nevertheless, go check that out if you can. And this week, let's get into it, I guess. This week,
so
we're discussing like the three big scientific
achievements in physics, I guess you could say.
Yeah.
Admittedly, I didn't get to do a lot of research on this.
Yeah, I mean, it's the holidays. I mean,
But I hope that we can at least talk a little bit about it. So, what are you gonna say?
Well, if they're not able to tell, for the audio listeners only, I guess we have a little cypress lemon tree here that serves as our Christmas
with some LEDs on it.
Our festive, with some LEDs. But anyway.
Yeah, so I guess what I wanted to do is talk a little bit about this. So Quantum magazine. Mm-hmm. They actually have a YouTube channel. I just realized
they
a couple
do?
days ago. Yeah, I didn't even know this.
Okay.
And they released a end of the year kind of synopsis of the big achievements in physics.
Yeah.
They also released ones on big achievements in math, computer science, and biology as well. Mm-hmm. Which I saw the math one, which is pretty good.
Okay.
And I'm sure the other two are great as well. But they had three in particular for physics. And the three were, number one was the end of the black hole information paradox. Number two was the, the room temperature superconductor. Mm-hmm. And then number three was the source of fast radio bursts. Mm-hmm. Number three, I didn't really get to research at all, so I don't know much about it. But, those are the three topics, I guess you could say.
And then number four, proving or disproving the existence of Santa Claus.
That's a reference to the Patreon
Patreon episode
podcast that came out on Monday. Or I guess not Monday. It'll be next week.
Yeah, it'll be in the next year.
Okay.
Right? Yeah, technically.
Next year,
Next year. But those three, those are, I mean, the first two are rather large to me. The third one, the question mark, what is it? They don't know, like a source of radio bursts, like where it's from.
Yeah, so I guess we can talk about that one first, since I didn't really research on that one anyway.
Yeah.
But the fast radio bursts, apparently it's like this, I don't even know why it's fast, honestly. I didn't get to even research anything on it, really.
We usually plan, like, if...
let's see if I can look it up.
Yeah. Well, I mean, I'm going off of stuff that I've read in some articles and then, like, just colloquiums and stuff.
Yeah.
The radio bursts, how planets like emit these radio signals. It can kind of happen when a star is going through it's like a transition, right? They emit light and different electromagnetic waves in the spectrum, right?
Well, let me read what it says on Wiki. Sure. It says, in radio astronomy, a fast radio burst is a transient radio pulse of length ranging from a fraction of a millisecond to a few milliseconds, caused by some high-energy astrophysical process not yet understood. Astronomers estimate the average FRB releases as much energy in a millisecond as the sun outputs in 3 days. So basically, what the Quantum magazine video was saying was that they believe that it could be from magnetars. And
that sounds like a Pokemon.
I think it is. Isn't it?
Yeah. Magnetars?
Something like that. Magnetar or Magmar. Something.
Magmar? Yeah, you're thinking about Magmar, bro.
Yeah.
That's an old head. You're an old head Pokemon fan.
Yeah, man. Original 151, was it?
Yeah, 151. Yeah, you know.
All right, so magnetar is a type of neutron star believed to have an extremely powerful magnetic field. hence the name. So it's from approximately 10 to the 9th to 10 to the 11th Tesla.
Oh, wow, those are huge magnetic fields.
Yeah, or 10 to the 13 or to 10 to the 15th Gauss. So the magnetic field decay powers the emission of high-energy electromagnetic radiation, particularly X-rays and gamma rays. So those magnetars are believed to be what are causing the fast radio bursts, but I believe that the researchers currently don't know if that's actually what is doing it.
Fascinating.
But that is the claim, I think. I'm not sure how they got to those claims. Unfortunately, I wish I would have researched it before this, but the magnetar is supposed to be the source of the fast radio bursts. So they believe that they might be able to map all magnetars in the galaxy with those fast radio bursts, or it's possible if that's the case.
Well, if I was paid to be a thinking man, I would say it's aliens. Easy.
I think you are paid to be a thinking man, Juan.
Case closed. I know. Yeah, I am. No, I'm not. I'm not paid enough to be a thinking man. So I'm only going to use that amount of capacity.
Oh, I see.
Think.
Yeah. It's got to be proportional to your pay scale.
Yeah, exactly.
I think it's already still out of proportion and not in your favor.
Yeah, I know.
Yeah.
But yeah, it's fascinating. Like I actually did not know there were whole ass planets that were, what are they called, magnetars?
Well, not planets. They're
stars.
They're stars. Stars. Neutron stars.
Yeah.
I don't know shit about astronomy.
Neither do I. It's not our forte.
So I can't really speak at all on this subject. But yeah, neutron stars are these real powerful stars I know, and I think they're also the ones that burst into supernovas. I want to say. Do not quote me on that. Big warning, because I'm not sure if that's true. But I think.
Yeah, maybe we can bring somebody on if anybody knows any specialists in magnetars and FMR. I mean FBRs.
Yeah, you mean FRBs?
I mean FRBs.
Yeah.
My dyslexia is kicking in. FRBs. Yeah, just
fucking big radio bursts.
Yeah. FRBR. Yeah. Yeah. Wait, no.
Or FBRB.
Damn it, happened again. Yeah.
The dyslexia.
The dyslexia, man. The food. The food coma that the holidays bring. You know. Yeah. That's fascinating. Honestly.
Yeah. Interesting stuff. So yeah, that was one of the ones that Quana had listed. But then the other ones that we kind of are more familiar, of course, is the superconductor.
Wait, Terrence, care to speculate more, dude?
Oh, what? The fast radio burst? Oh, in what sense?
Could it be an ancient civilization that?
You already know that's one of the things that they've already put out there.
I love it because there's probably YouTube channels dedicated.
I'm sure it is. You know that always happens when there's like some crazy event that's unexplained. Everybody wants to start saying alien civilization. They want to throw it in the mix, and then 99.99999% of the time it's never an alien.
And that gets like hundreds of thousands more views than the actual Quantum Magazine channel. Like
exactly.
Video. Yeah.
So yes, that speculation has been thrown out there already. I'm not gonna put my money down on that being the case.
We can't rule out anything, actually.
You're right, but I think magnetar is what they're believing is the case. Don't ask me how. I don't know.
Yeah, I'm gonna
maybe
guess
some astronomers in the comments. You guys can.
Yeah, please
enlighten.
Please enlighten us. What the source of these fast radio bursts could be.
Yeah. Although where's the podcast? We technically should be enlightening people. I said, although we are the podcast, so we should technically be enlightening the people, but.
Yeah, but this is not our forte. I have more to talk about in the other two. At least room temperature superconductors is something that I know about.
Yeah, true.
Yeah. But anyway,
so should we skip to
yes, room temperature superconductors.
Okay, so room temp superconductors. You guys know me and Juan are both descendants of condensed matter physics stuff. I say me particularly as descendant because I'm no longer a physicist, so I can't claim to be a physicist really anymore.
No, you can.
Can I though?
You're not practicing.
Yeah, but people have qualms when you call yourself a physicist. And you don't practice. You do.
I was the one that brought this up to you.
Many people have though.
I see. It's in the discussion.
Yeah, it's in the discussion. Like technically, I have a physics degree, a bachelor's in physics.
Yeah.
But people who are considered physicists all are like PhD level physicists and practicing. Like if you're a PhD level physicist, but you go into finance, technically you're still a finance person, not a
Yeah,
physicist.
you're not a physicist. Yeah.
Yeah, so
Well,
I don't know. I don't know the terminology, but
I would say if you're practicing, you are a physicist.
okay, yeah.
Yeah.
So I'll just say I'm a physics podcaster then.
Yeah.
Yeah.
Then you're
a physicist because you're practicing physics.
Because I'm practicing physics. Yeah.
But anyway, so we're from condensed matter, and of course the superconducting room, the room temp superconducting stuff is actually kind of close to our hearts because it's very relevant. It is condensed matter physics. It relies in that realm. And basically that's just saying, to recap, it's just a superconductor. So superconductors, basically, when they're cooled to low temperatures, certain types of superconductors, they exhibit zero resistance at a certain critical temperature. And that means that basically a current, they call it persistent current, can just keep flowing indefinitely. And yeah, you get a zero resistance current, which means that, for example, in practical application, it could be like if you have a telephone wire, like, right? Let's say if you have a telephone line from California to New York, then you would have no signal decay because that signal has no resistance. Therefore, it stays consistent the entire way. And that means you can reduce the need for things like amplifiers, for example, and you can just go straight off the pure signal. So no decay in the signal.
Yeah.
And so basically the room temperature version of that was achieved, which means that we don't have to use these crazy low temperature regimes in order to reach that zero resistance critical temperature.
Yes.
And yeah, the researchers though had to kind of skirt around the room temperature part though by trading it for these crazy insane pressures. So basically the room temperature superconductor that was discovered in the lab was made by compressing it or sandwiching it with these diamonds. So basically diamonds were pressing against it at these really insane pressures, I think in the gigapascal range, which allowed it to be able to even transition into the superconducting state without cooling it down to room temperature to low Kelvin temperatures. So I think the temperature it cooled down to was like 15, or it hit superconductivity in the regime of like 15 degrees C. Yes. I think. Yeah. So that's one of the major discoveries, I'd say, of the year, and potentially one of the biggest ones, honestly, for a while, until we can find how to bring down that pressure regime now. For room temperature superconductors.
Scale it back so that we can get as close to atmosphere as possible.
Yeah. And it's actually a big deal too, because some people didn't even, it wasn't even clear that a room temperature superconductor could even be possible, right?
Yeah.
So once they hit that, now it shows that, this actually is feasible. So that's actually a big leap. And if they keep going now, it also will help you to see, okay, which class of materials are going to be useful to even probe to try to reach these superconducting regimes, I guess you could say.
Yeah. Very true.
So yeah, and we've steadily been increasing along a kind of almost, I don't know if it's a linear trajectory, but there's a clear trend of the path that we've been taking to get to this room temperature superconductor.
Yeah.
There's different kinds of superconductors, type 1, type 2, type 3, I think even. Yeah.
Not to be confused with like the musical conductors, the super ones.
Funny guy.
Bad joke. Those are typically from Juilliard, Juilliard?
What, Juilliard for conductors?
Music. They're music school, right?
Yeah.
Those are super conductors.
But you can get conductors from many music schools.
Okay. But those are the super ones.
Yeah, true.
That's my argument.
I see.
Yeah.
Good job.
Thanks. It means a lot.
Good job.
Yeah. No, but I think it's overstated, I think, at this point, but it's one of the biggest. It would be one of the biggest technological innovations of this century.
Yeah.
On the order of magnitude of I think building an internal combustion engine, like that, those kinds of things where it would probably be as revolutionary as discovering electricity in some, or rediscovering electricity and stuff.
You know, I saw a cool video actually saying some of the applications of this room temperature superconductor, and I was like, oh, I didn't even think about this.
Yeah.
You could literally make like rail cars that float, where the rail is on top.
The rail's on top.
The rail, it's on top, and then
Why?
the car is on the bottom.
Oh.
Because you have quantum locking with superconductors.
True.
Right? So literally it can be locked into space, and it's like now instead of the rail car having to be on, below it, it can be above it.
Yeah, true.
That would be cool.
Oh, that'd be so cool. Yeah.
Yeah, you can do a lot of stuff.
Yeah. Yeah, you would still be limited by air resistance in that case, which you would still want tunnels and shit.
Yeah. I'm just saying you could do funny things like that, like
true
quantum locking it where the rail is above the rail car.
Damn, dude. That'd be amazing.
Yeah.
So spoiled. Y'all
spoiled on tech.
our Gen Alpha kids are going to be so spoiled.
Oh yeah.
This train doesn't even do quantum locking.
Yeah, right.
I remember when trains had
or like they're just going to be so lazy they don't even walk, like all the floors are just like superconductors. They got like room
superconducting tires. Yeah. Fine, I'll walk to school. Just glides.
Yeah.
Actually, it makes no noise because you just
right.
Yeah.
Just rolling down, just floating down the street.
Imagine how futuristic that's gonna look.
That would look very cool.
I'd be like, I want no part of this as an old person. Like, I'm gonna walk there. I don't need any fancy shoes.
The only problem, though, you'd have to make all the floors magnetic, which is already a bad idea usually, because you don't want to drop your phone and then now it's scrambled.
It'd be so cool to have a future where cars would be irrelevant. Do you think superconducting? I think it would probably.
You could do it. I don't know if we would want to, though. That's the thing, because like you have to remember, like if the floors are magnetic, then that means like you drop your keys, for example. Now you have a magnet to fight with to get your keys up, or if you drop your phone, that's destroyed now.
That's just comedy right there. It's not even a problem. That's just funny. Well, I guess I got to get a new phone. The phone industry is going to love it.
I'm sure they would. They definitely would.
No, but it would help the production of batteries, and like the electrical power grid is going to be. It's going to lower. It would change multiple industries. A ripple effect would be.
Yeah.
I think we've said, check our last video on superconductivity if you really want to hear.
What was it again? Do you remember?
It was our like hot take on them publishing that paper.
Do you remember what we called it though?
Yeah, I think it's called room temperature superconductivity achieved.
Okay.
But yeah, it's like a whole we like it's a hot take video. It's not really like us, like, how would you say, really delving into a full analysis of.
We haven't done really any analysis videos that much lately.
We did one on superconductivity a long time ago.
Yeah, but those were in the earlier days.
We've
been doing less analysis videos, but
true.
Been trying to do a little bit more of a different format of seeing how well the podcast can be with us just talking more freely rather than researching a bunch of stuff. And
yeah.
But actually, I think we might have to return to the form of researching. We'll see. I don't know.
Yeah,
this is a test. We're figuring it all out.
Yeah, true. It's growing pains. We're toddlers in podcast viewers right now.
Yeah, Joe Rogan says you don't even begin podcasting until you've done 100 episodes.
Oh, we're almost there though. This might be episode 99, dude.
No, this is like episode 97, I think.
You sure?
Yeah, I think so.
Okay. All right.
Not sure, but I'm pretty sure.
Okay. Yeah, I believe you. I mean,
so we're starting soon.
Yeah, we are. You heard it here first.
We're beginning soon.
We're starting. This podcast is just beginning.
Our first podcast is about to come. In about 3 or 4 more weeks.
Yeah.
Yeah, room temp superconductors, big changes. I don't know exactly. I'd like to make a list of all the things I could possibly conceive of one day of what room temperature superconductors could do, but I don't know.
Like a master list almost?
Yeah. Like what are all the possible things you could change? Like just think of like what would happen within like the fashion industry, communications, transportation, information technology.
Yeah.
Just go down the list.
I said it would impact quantum computing in some sense.
What would that be? Because they can build qubit computers or something?
Yeah.
Okay, yeah, because we use superconducting qubits right now. Yeah, so then you wouldn't have to do. Oh, but we talked about that last time, I think.
What did we say?
Because remember, we were like, I don't know if you could get rid of the the refrigeration unit stuff, because I think the refrigeration stuff might also have to do with the coherence times of the qubits.
Oh, true. Yeah.
Right. So you might have to have that still.
Yeah, very
even
true.
with a room temp superconductor. But maybe you can like reduce the amount of cooling you need or something.
Yeah.
I don't know.
True. Yeah. Oh, that's true. Yeah. Because you still need to thermally isolate the system, right?
Yeah, you might need to, or else you might get some kind of decoherence.
Yeah. Well, like superconducting, like container, essentially, because you know the Meissner effect, right? Where like it pushes out any
magnetic field.
Yeah, internally. So like if you put, well, I don't know, maybe.
Yeah.
I'm just thinking out loud.
Yeah, I think we don't know enough to say.
Yeah, I need to sit down and really ruminate over this.
Yeah.
But this is all leading edge stuff, so this is huge. I think if I were to redo my like graduate research, it would probably actually I debated this for a long time because my group does superconductivity. Because my group does superconductivity, but my advice, that's not where all the funding is. The funding is in like, how would you say,
in spin stuff?
The funding is mostly in like device fabrication and like stuff like that. That's like the moire pattern stuff, like all that. Yeah, that's like leading edge physics and condensed matter.
Yeah,
2D materials.
And the moire patterns for the audience is the stuff with the rotating graphene sheets.
Yes,
that came out recently, which was a big deal because people were finally trying to figure out what the hell to do with graphene.
Yeah,
and that upped graphene's credibility a little bit more.
Can't let it go, huh?
Yeah, they can't let it go.
The graphene, it's got to be promising. Yeah. There's somebody that definitely invested a bunch of money in graphene, and there's just sheets of graphene sitting in the corner of the lab. We got to do something with this. Bought all this. Yeah, actually, that's probably a good idea if you want to invest some money into something. Buy some graphene. Yeah. And that's all. Another investing tip. Another investing tip from someone who has zero money. Hey, I've been pretty good. Like, if I look at the history and I've told people like where to invest their money.
If you would have had money.
If I would have had money, I'd be rich right now.
Let's see where crypto's at. Crypto's been going up, man.
Oh, you sold or too early?
Well, I sold it in time.
Oh, okay.
But don't tell people about my
Don't tell people about what.
Because people love to send me crypto scams. To try to get my accounts and my
true
stuff.
I got a DM the other day. It's like, did you lose your I was like, how did you know I lost my wallet? Log in for Bitcoin.
They send me that shit all the time. Log into your Ledger wallet or log into this, and it's like a text message.
I'm like, if I knew how to get I know how to get my password back. But
you actually did lose your wallet for real?
Yeah.
Damn it, Juan.
Whatever, man. It's in the past.
See, I didn't lose mine. I just know that they always try to send me these fake messages to make it seem like I did.
Mm-hmm. No, I lost it, and it's one of my biggest regrets.
Damn. How much do you have on there?
I don't know. I bought
a lot or no?
I probably bought like two, a couple, good handful.
A couple coins?
Couple coins.
Okay. Damn.
Yeah, I know. It'd be $1,000
not great to
right
lose. Yeah, that's something you should find.
But that's when it was, black market money. That's when Ross Ulbricht was. Was the king of the black market.
Is that the Silk Road guy or something?
Yeah.
Good days.
That's when it was being used to buy illicit drugs and other very, very dubious kind of. What is the word I'm looking for? Just problematic stuff, sketchy stuff on the internet. The Wild West days.
Right.
Yeah.
Right.
Anyways, invest in. I would say if superconductors. Room temperature superconductors become a thing, invest in whatever material like
corresponds to that.
Yeah.
Well, graphene is going to correspond with graphite.
Yeah. So
because you make graphene sheets, I believe, by using duct tape or what is the tape? Scotch tape.
Yeah, Scotch
tape to strip off layers, right? Yeah. And then that results in a 2D sheet of graphene.
Yeah. So
which they can make nanotubes and whatnot out of.
True. So invest, and I will say most labs pay pretty damn penny for those kind of materials, like ultra high purity stuff. So, but like Alpha Azar, I guess would be because they buy their stuff, they refine their stuff, they get the raw elements from somewhere, and then they refine it at the lab. So, like I would say, just Wow, this became an investment podcast. But
yeah, we never stay on topic. Whatever.
Yeah, but I'm just
this
saying,
is our style, I think, maybe at this point.
I'm just saying, if you want to make some money, that's my brain. That's how my brain thinks. I'm like, you can do that. I'm not gonna do it because I have zero money. But maybe you can. Maybe kick back a little bit. That's a finder's fee for me.
Nobody's kicking back nothing to you.
Kick it back to the Patreon. Just, I'll be the lonely beggar in the streets. Yeah.
Right.
But anyway, the other one is what was it?
Yes.
They've ruled out the black hole paradox.
Yeah. So the other one says the end of the black hole information paradox. So the black hole information paradox, to sum it up, is basically what they're saying is. Information goes into a black hole, right? Mm-hmm. And we all know.
My brain, yes.
We all know that once the information passes the event horizon, it can't come out. Mm-hmm. So, Hawking and I think one of his students, I forget his name, like Bekenstein or something. They're working on this problem to figure out how that can be. And they discover Hawking radiation. So Hawking radiation is a consequence, I think, of relativity, I want to say. Yeah. Relativity combined with quantum mechanics. Mm-hmm. And it shows that black holes actually evaporate over time. Mm-hmm. So black holes will radiate will radiate particles over time, and it will decay, actually, until it evaporates completely.
Yeah.
Damn, I typed in coin market cap because we were talking about crypto.
And this takes eons. This is like a process. It takes forever. But somebody to illuminate. So I remember reading about this in my undergrad. It was about this AD. What is it called? The CFT.
Oh, anti-de Sitter space conformal field theory.
Yeah. So this is Juan Maldacena. Mm-hmm. His big contribution to the field. People called him this. He was like at one point. Actually, some physicists say he's still the best.
Yeah, I know he got a big
physicist of the day.
Jump from that.
Yeah,
isn't he the guy that works in the LHC too?
I don't know.
Or is that might be Nima or Connie Hamed? Those are the two guys I know.
Yeah.
That are kind of relevant.
But for the longest time, everybody was just like, "Yeah, Juan Maldacena is like the most brilliant physicist of this generation," because of
Witten's the guy.
Because of that contribution. Yeah, I think.
Even though
I don't know.
String Theory didn't pan.
I think Witten is a little more humble.
Yeah, I think.
Because I think he's also said like Maldacena's contribution is huge. Because Witten, I think his little theory.
M theory. Yeah, his little theory.
His little theory is
his micro theory.
I'm putting quotes on it, but like his theory is like it's something that hasn't really been. It's string theory, right? It's like something that might not even be
experimental evidence whatsoever.
Yeah. Well, Maldacena seems to agree. There is some evidence. There can be some evidence for strings. He said the LHC validated some of those findings.
Really?
But he said, it was like some old YouTube video. Maybe I'll give it to you and you can insert it in here. But
okay.
But like, he made the claim that string theory, like. At the foundational level, it can be proved, but the extrapolations can't, or something like that. There's some weird qualifications that he did.
Okay.
But people say he's the most brilliant physicist
alive
right now.
Okay.
But I say all that because that has to do with the black hole information paradox, correct?
Yeah, it did. I don't remember what the relevance was exactly, but you're definitely right. I remember reading it.
Yeah, what did they say on the?
Let's see.
Because
so I'll read from the wiki. It says the black hole information paradox is a puzzle resulting from the combination of quantum mechanics and general relativity. Calculations suggest that physical information could permanently disappear in a black hole, allowing many physical states to devolve into the same state. This is controversial because it violates a core precept of modern physics that, in principle, the value of a wave function of a physical system at one point in time should determine its value at any other time. A fundamental postulate of the Copenhagen interpretation of quantum mechanics is that complete information about a system is encoded in its wave function up to when the wave function collapses. The evolution of the wave function is determined by a unitary operator, and unitary implies blah, 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 blah. Information conserved in a quantum sense. So it says, as of November 2019, the paradox may have been resolved, at least for simplified models of gravity. So yeah, I'm not sure if it's been solved. I know there was a Forbes article that's saying that no, the black hole information paradox has not been solved. Of course, I don't read anything from Forbes because they have ad blockers, and I refuse to ever turn on my ad blocker, just out of principle. But yeah, apparently it's like still up for debate. People don't know if it's been solved for sure yet. But there have been some great strides, I guess, recently in which it could be possible it's been solved. But I guess it's really debatable whether these particular solutions to the specific parts of the problem are universally applied to the whole information paradox situation. Yeah.
Yeah, but how does the black hole information? So in English, I guess, like how does it translate? How does it all look?
So basically, I'm not exactly sure. It's kind of hard to understand, and it was hard for me to understand.
I mean, this involves quantum field theory for sure, like very deep concepts.
Well, it involved entanglement. I think really, if you just know quantum and general relativity, that should be enough. I just don't think I spent enough time on the problem to really internalize it.
Yeah.
But basically, what it showed was there's some kind of entanglement between particles, let's say, or I think they use entanglement as an example. Maybe I won't go down this road because I think entanglement is a way they proved it. But just to give you what's happening is basically one of the postulates of quantum mechanics is unitarity. And with unitarity, it means that with unitarity comes reversibility.
Yeah.
And that means that all states should be reversible, essentially. So it means that when information goes into the black hole, you should also be able to get the information out.
Yeah.
So you might ask then, like, how can you guarantee this postulate is correct?
Yeah.
And that's because we just know from the math that in order for quantum mechanics to work, your operators have to be unitary, right? Because you have imaginary values.
For physical observables, yeah.
Yeah, you can't have imaginary values exist. So by definition, for quantum mechanics to work, and it's pretty fundamental in the mathematics, you need to have a unitary operator, or else it just ain't going to work at all, right? To the non-math people I know, it's probably not very satisfying.
No,
but
not at all.
If you saw the math, you would understand it. Really, it makes sense.
Yeah.
So I don't know how unitarity replies in reversibility, but apparently that's the case as well. And since it's
is the reversibility condition more about like time reversal?
I think it is. Yeah. I think it is something along those lines. And I guess it's just because I don't know.
Meaning just like, but what I mean by that is like you run the clock back in the system.
Yeah, I think it has something to do with that.
Yeah.
So maybe it has something to do with time symmetry. I don't know.
Yeah.
I don't want to even speculate because I don't want to say the wrong stuff.
True.
But yeah, so with that, it's saying that once the black hole's evaporated, you should get all that information that was put into the black hole back. Stephen Hawking disagreed though initially and said that no, that's not the case because of some other three postulates. I think it has to do with the no-hair theorem they were saying, where it's like to fully characterize a black hole, all you need is a charge, the angular momentum, and the mass. And that fully characterizes a black hole. So Stephen Hawking, I think, was saying that that's all the information you need to characterize a black hole. Therefore, any information that enters into it is kind of irrelevant.
Yeah.
You don't have to get that back. But then the whole unitary part of quantum mechanics is saying that you do need to have the information somehow be able to be
conserved.
Yeah, to be conserved, because otherwise it means that the system's not reversible. Then you fuck up quantum mechanics, basically. Yeah. So Stephen Hawking didn't agree. He thought it was BS. But then, of course, the whole, what was it called, like Black Hole Wars or whatever with Leonard Susskind and whatnot, and another guy, I forget who else it was. They eventually proved that, the black hole does conserve information, and then you get the Hawking radiation leaking that information out again. But then to take it further with the black hole information paradox, there's another guy, I forget his name, maybe it's Page or something, who demonstrates a curve.
I would say that, so like this kind of has to do with like holography, because like with Madhusena's contribution, it was showing that like your information is embedded on the sort of two-dimensional surface of the black hole, right?
Yes.
And it's like this manifold contains all the information of like whatever physical like thing enters the system.
Mm-hmm.
And so that contains the black hole, in a sense, like embeds all that information onto this two-dimensional sort of manifold. It's two-dimensional space or whatever.
Yeah.
And
I'm not sure what all that means, but I know Leonard Susskind was the one who invented that approach, I'm pretty sure, the holography approach.
Yeah, and I'm reading here, this is the
ADS-CFT.
ADS-CFT correspondence, and it's called, and like you're saying, anti-de Sitter spaces, which are used in quantum gravity.
Which is QFT shit.
Yeah, but it's formulated
related to field theory stuff.
Right, it's formulated in terms of string theory or M theory. On the other side of the correspondence are the conformal field theories, which are quantum field theories, including theories similar to Yang-Mills and stuff like that.
I know nothing about any of that stuff.
Yeah,
like
this is all high energy. This is literally high energy physics, which is very outside of our realm, because I think high energy people have to do quantum field theory.
Yeah. This is all related to, like, if you want to do, like, if you're interested in like theories of everything and whatnot, this is the area you go to.
Oh, for sure. Yeah.
We don't know anything about this. Me and Juan are just me and Juan are like computer.
Condensed matter.
Yeah, we're lowy computer condensed matter guys who know stuff about computing and stuff like that.
Yeah, we know stuff about
science.
Electrons.
Yeah,
not about not about.
I don't know any universe fields and shit.
Yeah. That's so true. Like condensed matter people really just focus on studying electrons.
Yeah,
that's all we're do.
We're more pragmatic.
Yeah,
our stuff can be applied more readily in everyday life.
Sure.
The field theory stuff is more like that's getting into the realm of like grand, unified theories.
True.
Like the deepest mysteries of the universe.
True. Big
You're in
questions.
it for the love of the game, just strictly like figuring out like how the universe works.
Yeah.
Ours is more for like, okay, we're gonna get some cash out of this somehow. Like you could get a job at IBM or something with this.
True.
With the condensed matter skill.
Yeah. As opposed to, I guess, Well, high energy people like
they do too, but it's less practical for everyday industry jobs.
True, because you're literally reaching energies that are not.
Yeah, no one does this except physicists.
Normally, yeah.
Like who else would do this?
Yeah,
nobody.
That's true. But so in the ADS-CFT correspondence, it kind of invents the conformal field theory, and it's like apparently a well-behaved type of quantum field theory, but they're like these. Anyways, it involves string theory. Madhusena's like been touted to be a goat for this, and I would say so. I'm kind of getting into the applications to quantum gravity, because it kind of ties into like quantum gravity, why its impact is so important.
Okay,
but it also involves holography or whatever, or like the principle of like of I guess what is it called?
The holographic principle or something.
Yeah.
Yeah, I don't know anything about that.
Yeah, let me call up Susskind right now and see. Actually, Susskind would be an interesting guy to talk to, because he's one of the few rare American physicists, right?
Yeah.
There are not many of those.
He actually seems like he could be attainable too, because I see him on a bunch of physics podcasts. Like he was on Lex Friedman's. I know Lex Friedman usually gets some really good.
Yeah, but he doesn't. But I get the impression that he doesn't suffer fools either.
What do you mean? Like
Susskind?
We would be too silly for him, is what you're saying?
Yeah.
Yeah, maybe so. But he wouldn't even watch our podcast, so we could trick him into getting on. He'd just be like, "Oh, more physics podcast, sure."
Yeah. No, but I mean, like Susskind doesn't seem to really care enough. Well, not care enough, but he doesn't seem to. He likes discussing things, but that man is already like well into his like 70s. He's
probably
really
late
aged.
70s.
Yeah.
But I feel like we could possibly get him on if we really tried hard.
Yeah, I think we tried hard enough.
But I don't know if we want to go back to doing guests again right now. Maybe we could. Who knows?
Yeah. I think he would be more willing. If I ran into him in a coffee shop, I think I would charm him enough. It's like, yeah, that kid was funny. I'll go talk to him. Because, I mean, like, truth be told, like, there are very few, there are only a handful of, like, famous American physicists that I can think of that would get your that would get the sensibilities of
a real physicist.
No, of just being uniquely an American physicist.
Oh, I see.
Yeah.
Yeah. You're right.
You know, I hate to say it, but there is a
lack. Well, Eric talks about this. I think, did I mention this at one point?
Not on the podcast.
Okay, well, I was saying that, I don't know if I mentioned it.
Problematic light alert. No, I'm just kidding.
Well, basically, Eric brought to my eyes an interesting phenomenon where he was saying that basically the entirety of the science institutions, basically, the graduate institutions are manufactured to be at a scarcity of American students. And they did this so that they can have the H-1B, so they can bring in foreign students and basically have it so they can charge way less money for cheap, high skill labor.
Yeah, exploit.
Basically exploit graduate students. This is the beginning of exploitation for graduate students, right? Yes. And they can make it so that the laws, normal employee laws, don't even apply to you if you're a student.
Yeah.
Right? Like, when I left grad school, I was thinking that maybe I can get unemployment or something. And no, you can't do that. You can't apply for any of these basic things that normal employees get because you're classified as a different thing. You're classified as a student rather than an employee, or government employee or something. So, and they made this whole system basically so they can skirt around all these laws for cheap labor, high skill labor.
Yeah.
So it's just really interesting how that works.
Oh yeah, to the benefit, and then they're doing you a favor. I'm kidding. That's the argument. That's
right,
the argument.
Right. Of course, I'm sure they're justified somehow.
Yeah, we're exploiting you for your benefit.
Well, the thing they try to pretend is there's a major shortage of American students.
True.
Which Eric claims. I don't know if it's true or not, but I'm gonna the correctness of Eric has been so much, and I agree with almost all his stuff. So I'm just gonna take his. I'm going to naively accept his, or at least I'm going to naively at least talk about what he says because I believe it's most likely there's something to it.
I'm going to disagree with him with his theory on Santa Claus. I just want to say, shout out to our Patreon episode.
Well, I got to change the subject now. I got to tell the theory of Santa Claus.
No. Anyway, yeah. So you agree mostly with him, except with Santa Claus.
Yeah. But yeah, so he says that the shortage is artificial. And I think I agree because, I think I don't remember what I was saying exactly.
Just about the shortage of American college students.
Yeah, I think we would have more American students if we didn't have to abide by this H-1B stuff.
Yeah, that may be true. But then again, I mean, I would say that my class was definitely small. And the fraction of students in that class that went to...
But we could all go to graduate school, right? And maybe people would be more motivated to if they didn't have to compete with...
The best of the best.
The best fucking international students in the world. It's like... Yeah. It's like, damn, guys.
Cut us some slack, I know,
Seriously.
Right?
They've been doing this shit since they were like in 7th grade.
Yeah, the Americans
already got a master's by 22. It's like, damn, guys.
Can we get a break? That is so true. Like just being outcompeted by like people who were bred and whipped into like.
I mean, yeah, we can speak from experience. The people in our class were like, we've had people in our class who were like clearly beyond the material. They've already seen the material.
Yeah.
And they just know all the answers to stuff. And just like, why are you even here?
Yeah.
You already know all this.
Yeah, they did it. They did this shit for breakfast.
Yeah. And then it gives you more imposter syndrome. All the American students have imposter syndrome.
Yeah.
And then it's basically
they're not well prepared.
Yeah.
Yeah.
And then then they fuck up the curve for everybody. So nobody wins.
Yeah, the American system is kind of it's a weird Frankenstein, really. I think I think Eric might be right. I think I hate to say it, but it's
gotta get an eyelash in my eye. Sorry, man.
No, it's good. But it's like it's in a weird state right now, I think, because and that's something that I perceived even in my undergrad, just being like, wow, there's a lot of professors that are international, and then like coming into graduate school, not that there's a problem with that, but like coming to graduate school, I realized, oh, these are the best of the best people from their countries, and their governments are willing to pay a pretty penny for them to come here and learn and then go back.
Yeah.
A lot of them leave, but
but some of them stay. A lot of them.
But
stay.
the ones that stay are like really exceptional.
Yeah.
You know.
Yeah.
And so like
any professors are though, pretty much, because I mean, you already have to wait for a slot to open up in a university, right?
Yeah.
I mean, any university slot is going to be pretty damn competitive, especially in a 4-year institution, right?
Yeah.
So.
Yeah, and I will say it's a very big conspiracy, but to say, I guess, that the H1 system kind of like drives this like competitive like labor or wages, I guess, down for graduate students, unfortunately. But
well, that's the goal.
That's the goal. Yeah. I mean, yeah. I don't know. I don't know if it's I don't know if this is going to be a thing that's how would I say sustainable. But that's an important question to ask. I wonder if we could ask American physicists, like maybe even I was going to say Maldacena is also technically an American physicist because he's from South America, but like, but maybe more importantly, ask physicists who are like at these big American institutions like MIT, right? Because MIT is one of the premier
physics institutions.
Yeah, Caltech as well. Not Princeton. Princeton as well.
All the Ivy Leagues are going to be up there.
Yeah, but MIT in particular. Because I think Sluskin taught at MIT.
Did he?
Yeah.
I thought he was Stanford.
Was he? Maybe he is now. I remember him teaching somewhere. But you have a lot of. I would just love to sit down with one of those people, and just really just ask them about that kind of like, what is it about the American students that makes them so
shitty?
And I wonder if they see that. I wonder if they see the average American student just
Stanford.
lacking. Oh, Stanford. Okay.
Yeah.
But yeah, just anyway, yeah, just very interesting stuff, and contributing to this. The last I think great American physicist was probably U.S. was probably Feynman, right? At least that one.
Yeah, I think so. Yeah. I think that's the only one I can think of.
Yeah.
Yeah.
In terms of like contributions, like Nobel Prize contributions, right?
Yeah. I think that's the last one.
Am I tripping on it or no?
What, a Nobel Prize for Feynman?
Yeah. The last American physicist?
No, I think you're right, man.
Well, at least it's big of a contribution to physics, as much as he was touted to be like a great lecturer and also like contributed majorly to the field.
Yeah, I think you're right. I think that's it.
Yeah. As opposed to very much like a huge swath of international like
guys and gals who've won Nobels and Fields and all this crap.
But
all the rest pretty much.
Yeah.
Feynman might be the only guy. I'm trying to think who else is American that won.
That won
like Nobel Prizes. Yeah, I don't even know if there is anymore.
They probably didn't like the way he treated the Nobel Prize. He was just so like, this is so pompous and stuff. Yeah.
Well, he did say that. I think he said, I don't like awards, and I think they're, highfalutin and whatnot. But I don't know.
Maybe it's an American.
But he still accepted it at least.
Yeah.
Some people won't even accept their awards. Like, Perelman turned down his $1 million for the Millennial Prize problem.
The subway guy?
No, that's that's a different guy.
Okay.
That's the twin prime conjecture.
Yeah.
But Perelman was the Navier. No, not Navier-Stokes. It was the he was the I forget. It's the Poincare conjecture.
Oh, okay.
Yeah.
That's a big one.
I guess. I forget what it is even now.
But yeah.
Too complicated for me.
That's
all I know.
These are Millennium Prizes, Terrence.
Yeah. So I can't speak.
If you could redo your research career, what would you study?
Oh, but I still get to keep my knowledge or just redo it?
No, you still get to keep your knowledge, but
so I get to learn a whole new thing with my knowledge I have now.
Yeah, of course.
I'd probably go into more of the big universe question stuff.
Really?
Yeah, like conformal field theory, like because I'm really interested in trying to understand like Yang-Mills, geometry stuff, geometric algebra.
Mm-hmm.
Yeah, I wish I could learn more about that stuff. Like I just figured out. I only just learned about like geometric algebra this year.
Yeah.
like, and it has all these weird concepts I never even heard of, like bivectors and and like help, and I could understand more like manifolds and things. And
I just wish I got into more math heavy physics.
Take my math all the way to the end, you know,
to the edge.
Yeah, to the edge, because my math is like not even close to the edge.
I think the standard American treatment of, well, the standard physics treatment of math is very baby mode.
Yeah.
It's
like I don't even know what wedge products are, you know.
Nah, no clue.
And they're pretty important
mathematically. Like even physicists will kind of hand wave tensors and stuff like that. Like the average physics professor might be like, "Don't think about it too much."
Yeah.
This is how it works.
I think it could be really powerful if you became a mathematical physicist.
Yeah.
And I think I would like to go down that route if I could. Yeah.
Yeah, I think it's definitely one of the things that's when you're studying for the love of the game, like you're saying.
Yeah.
I think.
So I'd have to do that if I could restart and be young again, because I definitely ain't doing that shit now.
I think you are young. I think most physicists.
But my energy is not there. I can't be doing all that.
True.
And also I have bills to pay. I can't be spending time just learning for the sake of learning.
That's true. Yeah, you've been at this for too long, and you feel like
it's a wrap for me. I need to start actually doing things and getting money and
I mean the luxury of like a guy like what's his name Eric. I mean not what's his name. M theory.
Ed Witten.
Ed Witten, thank you. Jeez, Witten. The luxury of Witten, though, he had parents that were both physicists.
Yeah.
And
he started out with a massive advantage, right?
Yeah.
He had that scientific literacy at such a high level when he was a kid.
Yeah.
That's when you can do that kind of stuff, when you start out at such a good level.
Yeah. I would love to talk to him too. He's another kind of reserved American physicist, right?
Is Witten American?
Yeah.
Okay.
Yeah, his parents might. His parents might be immigrants, but he's definitely American.
Okay. Witten seems cool.
Yeah. He seems like a guy that would be have a lot of interesting things to say. Mm-hmm. But I mean, I would pick his brain about his experience and like what gave him, because he went into, I think he studied in his undergrad. He studied history.
Yep. Yeah.
And then he kind of just tested into a graduate program.
Right. I'm sure he was doing math all his life.
Yeah.
And then his break time was history.
Undergrad.
It sounds kind of like how Brian Greene was too.
Oh, really?
Because Brian Greene was doing math and physics all his life, and then he went into literature.
Oh,
so I think for him that was the college is the break for those guys who grow up with math and physics in their homes.
Oh, interesting.
And then they switch into,
So they
switch back.
I see. So that's like a professional.
Yeah.
Wow. So they kind of go into a graduate program like a serious.
Yeah.
Wow. So they just test in.
I guess so. It makes sense if you've been at that for your whole life, right? And you're just that far ahead.
I mean, truly, the graduate in the U.S., the graduate physics program is like realistically condense it down, distill it. You can really distill it into maybe a year's worth of physics, right?
Yeah, if you did it right.
Yeah,
I feel like programs like ours stretch it out absurdly.
The university, the American university system.
Yeah, like you don't need all that crap.
No, because I mean, think about it. You take quantum 1, quantum 2, ENM 1, ENM 2, a theoretical class or a classical mechanics, maybe 2 semesters,
and
statistical
mechanics,
and then 1 semester of statistical mechanics.
Yep.
You could do all those classes in a year.
Yeah, probably.
Yeah.
And
then that's truly the physics part. Maybe modern physics, maybe like a year and a half. Like, what I mean by a year is let's just say theoretically you could cram 3 semesters, because you can 3 semesters in a year, spring, summer, and fall. Right? Sounds brutal, but it's doable.
Yeah.
Like you could in theory.
Hell pay though. You'd hate your life for a year for sure.
But in theory, like I guess on paper, the stuff that we learn in the system as it is right now can be condensed into maybe a year and a half of physics.
Yeah.
2.
Yeah, I think so.
Which is wild, because it's not much if you think about crossing into a graduate or professional degree.
Yeah.
As opposed to international students, like we're saying, have seen this since they were,
high school and
in the womb.
yeah.
Since elementary school.
Since elementary school, they were reading
Professors
Griffiths.
like to say.
Yeah. No, literally, professors will say, like, I remember one of the wildest things one of the professors said was, like, he's like, you guys have done, he's like, contour integrals, this is, like, high school stuff.
Yeah.
I'm like, what are you talking about? Where are you from, man?
My teachers would say elementary school, like, calculus, this is elementary school.
And they weren't even kidding.
Yeah.
Like, they were. The sad part is they're not kidding. Like, that's really the most alarming
you guys are
thing.
cracked,
I'm like, excuse me? Like, what?
right.
Yeah. These guys, they need to have, like, the physics departments need to have, like, a sort of, like, what is it called?
A normal person?
A what?
A normal person? To keep these people in check?
No, they just need to sit all the professors down in one room and just tell them, like, hey, the students that your students aren't all like Einsteins, and I know they have great expectations, which is good and stuff.
It's good to be challenged.
It's good to be challenged, but the challenges have to be reasonable.
Yeah.
Like, you can't be, and a lot of professors fail at this, I think.
Right, I think so too.
The expectations of the students, but you got to really teach them.
You gotta survive though.
Huh?
You just gotta survive though.
I mean, ultimately, yeah.
Yeah. At the end of the day.
I mean, you know this now. Like, you just
survive.
It's not even about really learning the materials; it's about surviving through.
And it's not even really about even doing well. It's just surviving by the skin of your teeth as much as you can. Some people manage to do well. I don't know their secret, but
no, I've unlocked the secret.
for me, it's not.
I've unlocked
possible.
the secret.
That's good.
It's just doing it. You just gotta.
Hey, I
just do. That's what I used to do. Just do.
Just do it. Don't even think about it.
But you still got to think to do.
No, you do got to think to do it. But I'm just saying, like,
when I was in school, it was still possible. Not possible.
Yeah, but that's how you become one of the greats.
Yeah.
That's how you become a contributing physicist.
Yeah.
To these three big problems.
Yeah.
But yeah, I damn M theory, or you would do big.
Yeah. What would you do?
Big theories. I would say superconductivity.
That's cool.
Yeah.
So you want to stay in condensed matter, basically. Just go in another direction.
Yeah. I mean, for condensed matter,
nice.
you do need to learn some field theory stuff.
Yeah.
Like, you need to learn some
but
topology.
You don't need to do crazy stuff.
No, but you do need to learn some topology when you want to study, like, like Fermi surfaces and stuff, and then, like, higher concepts of, like, Berry curvature, and, like,
I see.
Study how all those symmetries can play into the, like, properties of a system and, like, weird physics.
Mm-hmm.
That's currently my problem. I'm like, man, I'm too lowly of a
math guy.
Too lowly of a. I'm a lowly experimentalist.
The theory.
We have to talk to a theorist. Strong. Yeah. It would take me a long time
to get there. Yeah.
To get there.
The theory is deep, man. People don't realize, man. Like, we've been doing physics for what? You now what? 9 years? Or 10?
Yeah, 9.
Okay, for me it was, I think, 8 or 7. I thought it was 8.
Maybe.
Yeah, and I feel still like I don't know shit. Like, I'm not even close.
No, you know a lot. I know
a lot. I know, but it's like the levels I could go still.
Oh, true.
It feels like endless. Like,
true.
Just so much I don't know.
Yeah, there's so much to learn.
Yeah.
So little time.
It doesn't end.
Oh, it never ends. I truly believe, like, I mean, I picked a good field, I think, to study, because I'm like, I can never get bored with this shit.
Yeah. You could just keep pivoting to new and newer things. And it doesn't stop.
Truly.
Yeah.
Like,
physics is great if you're a person who gets bored easily.
Oh, yeah. Yeah. That's why I kind of, like, was like, I think if I pick this up, it's going to be a lifelong thing.
Yeah.
Just really learning
it's
all
a
this
good
stuff.
hack.
It's a good hack for
ADD types.
Yeah.
Because you can go in so many different directions in the same field. Like, it will never stop.
And it's all, it's more like a breadth.
And there's big leaps too. It's not just like small, tiny little detail work.
Yeah.
It's like you can go big ass leaps if you really want to.
Yeah, because as long as you have the foundation, right?
Yeah.
Yeah. Which we all do.
Yeah.
We all have calculus, differential equations. We all have.
Yeah. But it's good. It's like, because you really can't get that for a lot of fields. Like, I don't know if you felt this when you were like in high school or younger, like you get massive leaps in like philosophy and things and like discovery of like using intuition and whatnot. But then over time, as you learn more and more, it just gets really tiny and your leaps aren't really that big.
Yeah.
And a lot of other fields do the same thing, but physics is like you can continuously get kind of giant leaps for things.
Yeah.
The knowledge is just so. It's just big pieces of knowledge to swallow. You can continuously go.
True.
So, what's our time?
Yeah, we're an hour.
Oh, okay.
So, but yeah, any final thoughts? I guess on.
I don't know. What interesting. I don't know. What interesting discoveries did you?
You're burping there.
Yeah.
You're like, bro.
What discoveries are you interested in this year,
Yeah.
or what did you think was interesting this year? Not necessarily physics, but
Yeah.
you know.
Well, they also did some recent, like, one of the longest teleportation experiments or something.
Oh yeah.
Yeah.
Quantum teleportation.
Yeah. But those always happen, you know.
Yeah.
Like
They just
break a
teleport more
record.
and more.
Yeah.
Kind of boring.
You
Cool, but boring.
Yeah. I mean, I guess it is. Yes.
Are you looking for something?
No, yeah, I was looking something up about just how the NSF just this year was just like, is teleportation possible? And it's like, yes, in the quantum world, but it's like,
Right.
I don't know.
Yeah.
Those are always kind of
Sensational.
sensational things. It's like you're making a copy of that kind of
Or it's not
of the state, no?
Well, you're not making a copy. You're just having two particles where one particle relaxes in some state and the other one relaxes in another state.
Yeah, but they're coupled.
Yeah.
Right.
You just know what it's going to be. I
Yeah.
guess. I don't know. I don't really understand it fully.
No, you understand it. We've done this. We've done this together.
Enough. Yeah, but this knowledge comes and goes, right? I got to
guess so.
refresh.
I guess
But
so.
anyway.
But yeah,
wrap it.
folks.
Yeah, so once again, guys, like, share, comment, subscribe. Check out the website, Eigenbros.com, Eigenbros on Twitter, Eigenbros Instagram, Eigenbros2 on TikTok. Thank you once again, Patreon people. And if you aren't on the Patreon, check us out, guys.
Yes.
30-minute podcast every week. Non-science if you want some more goofy stuff.
Yeah. A lot of fun stuff over there that happens.
Yeah.
So, yeah, check it out. And we'll see you guys next year.
See ya, people.